Hello, universe. Today I wanted to share with you a topic called optimal transport theory that I believe that every mathematician and physicist should know about. So let me first just briefly explain what optimal transport theory is, and I'll try to avoid too much technicality, and then let me explain why it's important for physics and math. So essentially what optimal transport is we look at the space of probability measures over, say, the real numbers, and we ask what is the distance between two probability measures. In particular, we want to know the cost of transporting one probability measure onto another. So the analogy which is often given in these textbooks is something called the earth movers problem, okay? Where you have a hill of dirt or a hill of sand with some volume, and you wish to transport this hill or this mound of dirt into a hole which has the same volume. And you know the cost of transporting each grain of sand. And so the problem is to determine the optimal way to transport the mound of dirt into the hole. And if you visualize the mound of dirt and the hole as probability measures, okay, so they're both some sort of probability measure with mass 1, then this question is equivalent to asking what is the cost of transporting one probability measure onto the other, okay? And once this cost is known, one can use it to define a distance, namely a metric, on the space of probability measures. So we'll define the distance between two probability measures to just be the cost of transporting one onto the other, okay? And it turns out this actually defines a metric on the space of probability measures. But this metric is extremely useful and fundamental toward our understanding of analysis. The reason is because it provides a more intuitive notion of distance than what was previously available, okay? So previously we understood distances between two measures. Let's suppose, for example, we had absolutely continuous measures with respect to the Lebesgue measure, so we can represent them as some density, let's say a Gaussian. Previously, we would understand if I have two Gaussian distributions on the real line, maybe with equal variance but whose means are separated by some distance, we would understand the distance between these two Gaussians via something called the total variation norm. Okay, where essentially we would subtract the densities, point-wise subtract the densities, and then take the L1 integral of this point-wise difference in the density. So it's called the L1 difference of the densities, okay? However, this is really measuring a vertical distance. So we're really measuring the vertical distance between the two Gaussians, but not the horizontal distance. The horizontal distance is much better captured by this metric provided by optimal transport. Namely, if I look at two Gaussians, then their distance with respect to this metric is definitely going to be related to their horizontal separation, okay? And so the reason why this is so important is that it allows us to use calculus of variations to derive a lot of physical laws, much alike to the process of Lagrangian mechanics, to derive a lot of physical laws from a more intuitive and geometric standpoint, okay? So now I'm going to get into the applications. So if we think about the heat equation for a moment, okay? One can show that the heat equation is the gradient flow of something called the Dirichlet energy with respect to the L2 norm, okay? So the heat equation is essentially an Euler-Lagrange equation associated to some energy functional. However, in optimal transport theory, the heat equation is the gradient flow of the entropy functional with respect to the Wasserstein metric, or the Wasserstein norm, which is provided by optimal transport theory. Why is this important to physics? Well, this is a big deal. This is a big deal because the entropy, the gradient flow of the entropy is, in physical terms, should be the heat equation, like based on our understanding of thermodynamics. When you apply the heat equation to a mass distribution, what you expect is that this is the way to maximize the entropy of the distribution locally. And that is exactly what this theory enables us to prove rigorously. Okay? More than that, there have been results relating optimal transport theory to the study of curvature. So it turns out that you can do optimal transport on a manifold. And in Euclidean space, if let's just picture I'm transporting a Gaussian distribution, then, the Gaussian distribution transported from one location to another might have fixed variance, okay? In the path which optimally transports it from one location to another. However, if I introduce a curvature, if I introduce my ambient space as a manifold, then the curvature of the underlying manifold is going to influence the variance of the Gaussian distribution as it moves from one location to the next. And so by studying the curvature of the manifold, we can better understand the interpolation geodesics between different measures in optimal transport theory, and vice versa. Namely, our understanding of optimal transport could provide insights into curvature in Riemannian geometry, which were previously inaccessible. And so this is getting used in the theory of general relativity. And this is really recent. There are a lot of papers being published by prominent physicists and mathematicians in the field of general relativity that are using optimal transport theory. But not just general relativity and not just thermodynamics. Optimal transport has been used in this paper here called The Free Time Evolution of the Quantum Wave Function and Optimal Transportation by Laura M. Morato. Hopefully you can read that. Okay. This paper essentially derives the Schrödinger equation, which is equivalent to a system of fluid dynamical equations called the Madelung fluid equations. It derives the Schrödinger equation as the gradient flow of an entropy functional, which from a stochastic generalization of optimal transport. Okay, so essentially, optimal transport can be generalized in a stochastic setting and used to, in a similar way, to provide variational analogs or variational descriptions of key equations such as the Schrödinger equation. Okay, so in other words, this geometric understanding of the probability measure space enables us to provide variational and geometric descriptions of PDE as Euler-Lagrange equations of critical energy functionals, which is one of the main goals of physics. In particular, classical mechanics, if you think about Lagrangian mechanics, classical mechanics is filled with this type of reasoning, where essentially we view the Newton's laws of motion or the evolution of a system as some optimal or some minimization of an action functional, right? So the classical trajectory of the system is the trajectory which minimizes the action, and so there is an infinite dimensional generalization of this called the Benamou-Brenier fluid dynamical formulation of optimal transport, which basically embeds all of classical mechanics as the motion of these Dirac delta masses. So probability measures, which are Dirac delta masses, are basically point-like particles, and all of classical mechanics understands the evolution of point-like particles according to Newton's laws. And so these laws of motion can be embedded within the probability space as just trajectories of these Dirac delta masses. And this can be successfully embedded actually quite easily into the theory of optimal transport. But in this more general setting, we allow for a description, a variational description of the time evolution, classical time evolution of arbitrary mass distributions. Which means that if I throw this book across the room, I could model it using classical mechanics as a point particle moving across the room and then model its motion according to gravity. Or I could do the same underlying physics, but model this book as a literal mass distribution with some volume, some finite volume, and some spatial mass distribution, and understand how the entire spatial mass distribution evolves throughout time using the same variational techniques of classical mechanics in this infinite dimensional setting. And the key is just the metric provided by optimal transport theory. So I'm not kidding when I'm saying this is a very big deal. It allows for a lot of geometric intuition and a lot of new results in geometric partial differential equations are stemming from this metric provided by optimal transport theory. Okay? So, for those of you who want to check it out, I'm going to post a video recommending optimal transport textbooks. But for a first introduction, this textbook that I have right here by San Ambrosio called Optimal Transport for Applied Mathematicians is a great place to start. And also check out Cedric Villani's Topics in Optimal Transportation textbook and read the introduction. It should be available online as a free PDF. I also have resources on my website, mathsheets.com. So if you search up mathsheets with a Z at the end.com, I did a lecture at my university on the Kantorovich problem, which is one of the key introductory topics when you're first learning optimal transport. And I put my full lecture notes on my website. And so I compiled a lot of results from different textbooks and put them on my website, so you can check that out as well. And yeah, I hope you all take a look at this topic. Some buzzwords that you can look up on YouTube are Earth mover's distance, Kantorovich-Rubinstein distance, and Wasserstein distance. Okay? So if you look up those buzzwords on YouTube, you'll find some good videos kind of explaining the basic intuition about the Earth mover's distance, which is essentially provided by optimal transport theory. And I this theory really enlightened me, and so I just really wanted to share it with y'all because it seems like a lot of you really care about math and analysis, and not many people have heard of this, and I really think that I was blessed to learn about this theory, and I wanted to share that with y'all. So anyways, have a nice day.